Hey, have you ever been stumped by a mechanics problem where the force isn't constant but changes over time? Well, you've come to the right place. Today, we're going to tackle a classic problem from Irodov that trips up a lot of students. But stick with me, and by the end of this, you'll see it's totally manageable.
Okay, so let's get into it. This is our puzzle for today, straight out of Irodov's famous problem book. Now, I know it looks a little intimidating with all those variables, a, t, tau, but trust me, it's not as bad as it seems. We're going to break it down piece by piece.
Here's the game plan. First, we'll just figure out what the problem is actually describing. Then, we'll find the one key physics idea we need to crack this thing open. After that, we'll solve part A for momentum, then part B for distance, and to finish up, we'll pack all this into a little toolkit you can use for any problem like this.
Okay, first things first. Before we even touch an equation, let's just get a really clear picture in our heads of what's going on. Honestly, this is the most critical step to solving pretty much any physics problem.
So what do we got? We have a particle, mass m, and it's just sitting there, not moving at all. Then, for a set amount of time, from t equals 0 up to some final time we're calling tau, it gets pushed by this interesting force. Our mission is to find its momentum right when the force shuts off and the total distance it moved while the force was on.
Now let's really look at this force. See that little t inside the equation? That right there is the big clue. This is not a simple, steady push. This force is alive, it's dynamic, its strength is changing every single moment in time.
So before we get lost in the math, let's try to build some intuition. Just imagine you're this particle. What would this push actually feel like from start to finish?
This timeline lays it out perfectly. Right at the beginning, at time 0, there's no force. It's a really gentle start. Then it starts to ramp up, getting stronger and stronger, kind of like slowly pressing down on a gas pedal. It hits its peak strength exactly halfway through the journey. And then it does the exact opposite. It starts to ease off, getting weaker and weaker, until at the very end, it's back to 0. It's this smooth wave of force that swells and then fades away.
All right, section 2. Now that we have a feel for what's happening, we need to dig into our physics toolbox and pull out the right tool for the job. And believe me, for a force that changes with time, there is one master key that unlocks everything.
Okay, stop right here. This slide shows the #1 trap that students fall into with problems like this. It is so tempting to just use F equals ma. We all know it, we all love it. But it only works if the force, F, is constant. Our force is changing every instant, so F equals ma is just, well, it's the wrong tool. We have to use the more fundamental, the more powerful version of Newton's second law.
And this is it. This is our master key. Force is equal to the rate of change of momentum. What that really means is that a force tells you how quickly an object's momentum is changing at any given instant. This formula is always true, whether the force is steady or, like in our case, all over the place.
And the real beauty of this master key is how it gives us a direct path to the answer. If the force tells us the rate of change, then to find the total change in momentum, we just have to add up all the little changes over the entire time. And what's the fancy calculus word for adding up a bunch of tiny pieces? You got it, integration. This idea is so important it has its own name, the impulse momentum theorem. Okay, we've got our key, we know the plan. Let's go unlock the first part of this puzzle and find that final momentum.
So, we start by literally just taking our force equation and plugging it right into the integral we just talked about. The total change in momentum is just the integral of f dt. And since the particle started from rest, its initial momentum was 0, which makes things easy. The final momentum is just whatever the value of this integral is.
Now before we integrate, let's make our lives a little easier by multiplying that at through the parentheses. Okay, now we just have two simple terms. This is just straightforward power rule integration, nothing fancy. The integral of t is t squared over 2, and the integral of t squared is t cubed over 3. Easy enough. So now we just need to evaluate this at our limits. We plug in the top limit, tau, for every t, then we plug in the bottom limit, 0, and subtract. Of course, plugging in 0 just gives us 0, which is nice. So we're left with a tau cubed over 2 minus a tau cubed over 3. A little bit of work with fractions and we get our result.
And boom, there you have it, the solution to part A. The final momentum is a tau cubed over 6. And yep, that matches the answer key in Irodov exactly. Part 1 is down.
All right, on to section 4. Let's find that distance. Now, this part takes an extra step, but it uses the exact same ideas we've already mastered. No new tricks here, just putting our tools to work one more time.
Now, you can't just jump directly from force to distance. You have to take the stairs. That first integration we did was like going up one flight, from force to momentum. From momentum, it's just a tiny hop over to velocity, right? Since P equals mv. Then, we have to climb a second flight of stairs. That's our second integration to get from velocity to our final destination, distance.
First up, we need to know the velocity at any time t, not just at the end. So remember that momentum function we found before we plugged in the limits? We need that again. We just take that whole expression, and since p equals mv, we divide it by the mass m to get our function for velocity over time.
Okay, here we go. Time for our second integration. The total distance traveled, s, is just the integral of that velocity function we just found. And again, we integrate from our start time, 0, to our end time, tau. It's the same deal as before, just using the power rule. T squared becomes t cubed over 3, and t cubed becomes t to the 4th over 4.
And that's pretty much the last step. We plug in our limits. The lower limit of 0 gives us nothing again, so we just evaluate at tau, which gives us tau to the 4th over 6 minus tau to the 4th over 12. A quick bit of subtraction, and that simplifies down. And there we have it. Our final answer for distance is a tau to the 4th over 12 meters. Problem solved.
Awesome! We solved it. But listen, getting the right answer is only half the battle. The real win is understanding the method so you can walk up to any other problem like this and know exactly what to do. So let's wrap up with the key takeaways.
Think of this as your guide to not falling into the common traps. First and foremost, I'm going to say it one more time, do not use F equals ma for a variable force. Always start with F equals dp by dt. Second, pay attention to the initial conditions. Here, starting from rest made our lives way easier. And finally, just remember that staircase. Force to velocity to distance is a two-integration journey.
And look, this whole process isn't just for some abstract problem in a textbook. Think about it. The thrust from a rocket isn't constant, right? It changes as it burns fuel. Or when you're accelerating in a car with a manual transmission, the force changes with every gear shift. You could use this exact same calculus toolkit to analyze those real-world motions. And that's when physics really starts to get cool.